Okay, everybody, let's get started again. We've been talking about the fact that strong acids have stable conjugate bases. So now our question is, what makes a conjugate base stable? Or what makes a stable conjugate base? And the first principle we looked at was electronegativity. But I want to remind you of the context that we're dealing with. We're talking about electrons and how high or low they are in energy. There's two different things we need to be aware of. One is potential energy. That's related to proximity to the nucleus because of Coulomb's law. Closer to the nucleus is lower in potential energy. But then we've got to deal with kinetic energy, which you might think is how fast the electrons are moving, but is really the spread outedness of the wave function. Electrons that are spread out in space more, their wave function slope changes less, kinetic energy is therefore less. So we're going to have these two different effects, and we're seeing an interplay between them as we talked about going across a row of the periodic table. We said that effective nuclear charge increases, so atomic size, the atom that holds the negative charge, is smaller. That means that the negative charge is held closer to the nucleus, which should be lower in potential energy, right? Now, at the same time, as you get closer to the nucleus, the wave function's not quite as spread out, and so kinetic energy should get higher. That's an offsetting effect. Within a row of the periodic table, the changes in kinetic energy are small. And actually, the changes in radius are small, too. So the dominant effect within a row of the periodic table is this electronegativity effect, which is related to distance from the nucleus, which is a potential energy argument. Okay? Now, and we rationalize this, or rather we use this to say, hey, electrons on fluorine are actually lower in energy than electrons on carbon, and that allows us to make some predictions about what kind of molecule will be more reactive or more nucleophilic than another. But some of you have pointed out that the electronegativity argument doesn't always work. And so if we go down a row of the periodic table and compare the halogen acids, HF through HI, the pKa's are 4, minus 7, minus 9, minus 11. If we draw the conjugate bases, F minus, Cl minus, Br minus, I minus, it actually turns out that iodine is way less electronegative than fluorine. And that's exactly what you would expect in terms of effective nuclear charge, because the valence electrons on iodide are shielded from the nucleus by all the other sets of filled valence shells, and so they don't experience as much of an effective nuclear charge, and therefore they can be more spread out and are held further away from the nucleus. So what I'm trying to say is that electronegativity doesn't do the explanation here, because if it did, you would predict HF would be the strongest acid, and it's simply not, and not even close, right? By a factor of 10 to the 15, 100 trillion times more acidic. Okay, so what else changes? Well, size changes, and again, the argument about effective nuclear charge is one that will work for us here. Higher effective nuclear charge, lower, I'm sorry about the penmanship, effective nuclear charge. I'm not sure which ways my arrows are supposed to go, so I apologize if I'm being inconsistent and going from low to high instead of high to low. The consequence of the lower effective nuclear charge for I minus relative to F minus is larger size or radius, I guess, and we could say smaller size. Okay? Now, larger size should be accompanied by increased distance from the nucleus and therefore higher potential energy. Okay? So again, and that's really an electronegativity argument. So you might be saying, well, shouldn't the electrons on F minus be lower in energy just because of potential energy? Sure, but you can't forget kinetic energy. So what is the kinetic energy effect? That is, if you are spread out, if the wave function is more spread out in space, the wave function has lower kinetic energy. And we'll call this maybe a compact wave function versus a spread out wave function. Okay, so I minus is the more stable conjugate base due to low kinetic energy due to the spread outedness. That's not a word. Spread outedness of the wave function for iodide. Okay, so what we're saying is that within a row of the periodic table, the potential energy effect dominates. That's electronegativity. Down a column of the periodic table, the kinetic energy effect dominates. That's size. Okay, larger. Go ahead.
So another question: like if we have multiple factors at play, for example, for carboxylic acid or ethyl group, the ethyl group often has sulfur, which is bigger than the carboxylic acid as the resonance within the oxygen.
Yes.
So lower pKa. So when there's multiple factors, how do we? Yeah.
Okay, right. So the question is, what if I mean, if I ask why is iodide more acidic than fluoride, that's a straightforward comparison. But if I do something like, I would even say, without throwing resonance in the mix yet, I would even say it would be kind of a unfair comparison to ask, I mean, I happen to know this pKa I think is around 8 and this one's around minus 11. What is their difference in size versus what is their difference in electronegativity? That's, I don't know. That's hard to say. So really, you're going to be making comparisons where there's a big difference in just one factor. All right. Other questions? Go ahead. As you go down a row of the periodic table, you go from smaller and compact wave function to larger, more spread out wave function. That's from high kinetic energy to low kinetic energy, and that effect dominates going down the row. Because the size differences down the row are pretty big. All right. So if I were to tell you, for example, to make some predictions about the following molecules, I don't know about hydrogen sulfide or hydrogen selenide. Actually, hydrogen sulfide is rotten egg gas. That stinks. I don't know about hydrogen selenide. Thankfully for all of us, water does not stink. Which, based on the size argument, which is going to be our strongest acid? The hydrogen selenide. Why? Because its conjugate base, there we go, is the atom that holds the negative charge in the conjugate base is larger, and therefore those electrons have lower kinetic energy. Go ahead. Yep. Yes, it's a stronger acid because its conjugate base is more stable. which makes it less problematic to lose the proton. All right. Yes? Further right I go, I get more acidic. Further down I go, I get more acidic. Yeah, that'll work. Yeah. Okay. So those are two sort of principles, and they're related to potential energy and kinetic energy. The remaining couple of things that we'll talk about are also related to kinetic energy and or spread outedness of electrons. Okay, so I'm going to call item C inductive electron withdrawal. I'm not sure what your text calls it, but the basic principle is this. Let's compare a carboxylic acid in which all of these groups are where you've just got a methyl group. And then let's add, instead of protons, let's add fluorines. Let's draw the conjugate base. Always draw the conjugate base. And I will go ahead and tell you the pKa's. This one's 4, this one's, I forget, but let's just pretend it's 2. Okay, so the trifluoroacetic acid is more acidic, which means its conjugate base is more stable. All right, why is that? Go ahead. Okay, the fluorine can help pull the negative charge. How does that work? It's an extended sucky effect. It's one of our favorite family jokes. This vacuum really sucks, and you don't know whether it actually works or doesn't. And then Buddy the Elf, ooh, it's very sucky. Sorry. Yes, so fluorine's more electronegative than carbon. You learned in general chemistry what that means is the bond is going to be polarized with electrons. I'm drawing a symbol for a dipole here. The positive end of the dipole has a little cross. The negative end of the dipole has an arrow. Each of these carbon-fluorine bonds is polarized. That makes this carbon, therefore, electron poor. We'll put a delta plus there to indicate that it is now electron poor. Owing to the fact that it is now electron poor, it will pull electron density away from the neighboring carbon, which will pull somewhat electron density away from the neighboring oxygen. Not a huge amount, but it's enough to spread out the negative charge. And spreading out the negative charge, that's a kinetic energy effect. It lowers the kinetic energy of the electrons and makes them more stable. Because this happens it has nothing to do with the electronegativity of the atom that bears the negative charge in the conjugate base. That's actually identical. It also has nothing to do with resonance. We haven't talked about resonance as a reason yet, but the negative charge is delocalized on both of those oxygens, and that's true for either case. So it's not that one either. It's the fact that you have electronegative atoms nearby that are creating bond dipoles that are, through the network of sigma bonds, literally tug-of-warring electrons a little bit away from where the negative charge is. Okay? Incidentally, this is also why earlier I alluded to the fact that in an amino acid, the pKa of the carboxylate proton is lower. It's also around 2, and that's again because of the electronegative effect of the nearby amino group. Okay, so Ethanol versus trifluoroethanol, which is the stronger acid? The one with the fluorines nearby. Yeah?
Did you ever ask us to compare like two atoms together? Like
Oh, sure. Could I ask you to... That's an excellent test idea. I'm sorry. Now I'm going to make your life miserable, right? Yeah. No. Last semester, I was showing the students a interesting reaction, and somebody asked, "Could you do that in a 6-membered ring?" And I said, "Good, Anakin, good." So yes, your journey to the dark side is not complete yet, but it's getting there. No, I'm sorry, but yeah, that's. I'm really sorry. I hope I didn't cause any problems. I'm just trying to be silly, but anyway. Yes, you would be able to predict that this one would be more acidic than that one simply because of electronegativity. Did I push a button? Suddenly the lights went on. Okay. Yeah, you'll have a periodic table on the test. More acidic, less acidic. And that's because chlorine's less electronegative than fluorine. And remember, this effect has to do not with the atom that holds the negative charge, but rather the electronegativity of nearby atoms and the through bond tug of war. So perhaps the confusion is when we were talking about the negative charge in the conjugate base being on the halide, electronegativity didn't matter anymore, only size. But here we're not talking about where the negative, we're not talking about the size of the atom that bears the negative charge. That's identical in these cases. We're talking about the ability of nearby groups, because they are electronegative, to pull electron density away from the negative charge through the bonds as sort of a tug of war. Yeah? Yeah, is there a distance where this becomes less significant? Sure. Can I predict where that would fall off? Do I happen to know? No, but you could predict a trend, right? You might say, oh, well, closer is better, so most acidic here, less acidic, least acidic. And you're right, at some point it stops mattering. All right. Lastly is, oh, shoot. I missed something on electronegativity that we don't need to belabor. I will just say that protons that are on sp3 carbons are less acidic than protons that are on sp2 carbons, and those are less acidic than protons that are on sp carbons. The reason for that is that in the conjugate bases, the electrons on an sp3 carbon are held in an sp3 orbital. In an sp2 carbon, they would be held in an sp2 orbital, and on an sp carbon, they'd be held in an sp orbital. Remember, s orbitals are closer to the nucleus than p orbitals. So the more s character a hybrid orbital has, the lower in energy it is. That's a potential energy argument. Frankly, if you want to remember that greater orbitals with greater s character are more electronegative, that's fine. sp carbons are more electronegative than sp2, which are more electronegative than sp3. So that's a related principle. We don't need to spend a huge amount of time on it, but oh, and that was even, that's not electronegativity, that's size. So we need to copy and waste time. Salud. All right. Okay, finally resonance, and this is an, go ahead.
Sorry, so the SP one is more acidic?
Yep. Yep, the alkyne is more acidic than an alkene, which is more acidic than an alkane. And it's because the orbital that holds a negative charge in the alkyne has more s character and is therefore lower in energy. All right, so resonance is the next big concept that we need to explore. I asked you earlier on in the class to be prepared to draw resonance structures and understand the rules of drawing resonance structures so you don't make mistakes. We've already dealt to some extent with this issue. If you compare, I just heard the words Texas carbon. Did I draw a Texas carbon? Did you find? Did I? Okay. What is a Texas carbon? Well, it is a carbon bonded to 5 things. Yeah, because everything's bigger in Texas except carbon, which still can't be bonded to 5 things in Texas. Sorry. All right, let's compare ethanol with phenol. We've sort of done this before. If we compare pKa's, I didn't mean that. The phenol pKa is 10. The regular alcohol pKa is 16. If you compare conjugate bases, the reason for this difference is the fact that in the conjugate base of the ethanol, the negative charge is localized on the oxygen, whereas in the phenol, the negative charge is delocalized. I can draw resonance structures in which I put the negative charge from the oxygen no longer on the oxygen, but in the benzene ring. By the way, if the word benzene is not familiar to you, that is a 6-membered ring with 3 double bonds in it. We'll talk more about it later. But the basic principle is, if I have lone pairs or a negative charge adjacent to a pi bond, that's a situation in which I can move the lone pair over to form a new pi bond with the adjacent atom. If I stopped there, I would have too many bonds to carbon, so I need to then move this pi bond electrons over here to the adjacent atom so that I don't break my Lewis structure rules. And in so doing, I find that now the negative charge is on this atom instead of it being on the oxygen as it used to be. And so I could go around the ring, make a new bond here with the adjacent atom, and then break this pi bond and move it to a lone pair on the adjacent atom. Then I would get to this resonance structure. So far I've demonstrated that the negative charge is in those places. And then finally, as I go from here to here, I show that I've got 4 different places the negative charge can be on. Yeah?
I just have a question about drawing these, because you draw the arrows. I don't know, if you write and you have to always draw the arrow going from one thing next to it, or you draw okay, this is the wrong pair going over.
Okay, good. Yeah, so these are some rules of Lewis structures and arrow drawing that we haven't talked about, I think, explicitly. And even now, we'll go ahead and keep it G-rated for everybody. No? Yeah, sorry. Lame. Really, really lame, apparently. Yes, so the rules of drawing arrows are arrows must start with a lone pair or with electrons. They always begin with electrons. The arrowhead must always end either at a nucleus or in the space between 2 nuclei to indicate the formation of a bond. Now with resonance involves, we need to talk about the molecular orbital origin of resonance really before you understand the why behind this. But in resonance, you can move lone pairs to form a bond between the atom that held the lone pairs and the adjacent atom. but it is not okay to pick up those electrons and draw a squiggly arrow all the way over here. So it's sort of the negative charge two-step, I call it, with resonance and negative charges or lone pairs. You can move this lone pair over to make a pi bond with the adjacent atom. And then what you do next depends on what this atom is involved in. This atom is involved in a pi bond. If I stopped there, I would have 5 bonds to carbon. That's too many, so I have to then move this lone pair away from the bond, and the only place I can move it is here on the adjacent atom. Now, some of you may be saying, well, couldn't I just interchange between the resonance structure here on the left with the one all the way over on the right? I mean, couldn't I do flip, flip, and flip? And the answer is yes, but that's sort of pro-level resonance arrow flipping, which achievements you have not yet unlocked. So I would suggest that you don't try to do that at this stage. Keep the steps simple. Don't try this at home. Certainly don't try it at home. Certainly don't try it on the exam. Stick with the regular two-step of arrows, right? So the reason why phenol is more acidic than ethanol is because the negative charge in the conjugate base of phenol is delocalized. And that's, again, a spread out argument and ultimately a kinetic energy argument. Lower kinetic energy by being spread out through space more. Yeah?
I was just wondering if there's like a the atom, which one's more priority?
Okay.
Oxygen and a hydrogen versus like a carbon that's like has resonance and is conductible.
Okay. Yeah, it's a good question. And the question, just to repeat it, I think, is we've got various effects: the inductive effect, electronegativity of the atom that holds the negative charge, size of the atom that holds the negative charge, and then resonance delocalization. Which matters more? And I would say, I mean, ideally, it'd be lovely to have a decision tree. However, at a certain level, instead of trying to predict it, you just go into the lab and test it, and then you see. That's what the scientist does. Notice that what I'm not doing here is I'm changing in this comparison, I'm changing the fact that there's resonance down here and there's not there, but I'm not changing the atom that holds the negative charge. Yes, will that hold true on the test? Yeah. So in other words, I would not expect you to predict whether this is more acidic than this, or maybe a better way to say that is I would not expect you to predict which is more acidic, phenol or this thiol molecule, right? Because this one doesn't have resonance, but the atom that holds a negative charge in the conjugate base is bigger. So how do those offset each other? I happen to know the result. I happen to know that apparently size is the more important factor here, but that would be difficult to predict, right? So, yeah. So you're going to be looking for the one difference, okay? Right, if it was just the O switched out with the S, as long as everything else remains the same, that's a simple prediction. For example, let's take thiophenol instead of phenol. Without even knowing the pKa's, right, you could make the prediction there's resonance in both of them, but you've got a difference in atomic size, and so this thiophenol should be more acidic, and it is. Yep. Okay. So, and how do I ask questions about resonance structures? I like to give you problems that make your brain sort of temporarily want to quit working. And then, but if you try to take a deep breath and calm down, you can, yeah, figure it out, okay? So I've often asked the question, which atoms, there's not an I in atoms, which atoms share the negative charge on the oxygen via resonance? Would it be all of them? No, only some. So what usually happens when, if you haven't had a lot of practice on problems like this, is what I call the Spongebob Effect. So I don't particularly like SpongeBob, but it wasn't really a thing, but it sort of happened while I was out on my mission. My sister kind of enjoyed SpongeBob, so here is... Anyway, I don't know why we're taking valuable time to draw SpongeBob, but now we're in for a penny. We ought to just continue and draw his pants and everything. Anyway, there's an episode apparently where somebody asks poor SpongeBob, he sees somebody and he doesn't know the person's name. And it cuts to a scene in SpongeBob's brain where there's all these little SpongeBobs running around and they're sorting through filing cabinets, there's papers everywhere, and then suddenly things are on fire, right? And this is what happens when... That's really creepy. I'm actually getting rid of him. Anyway, so the SpongeBob brain on fire effect takes... When you see something like that, it can cause trouble, and you can just... You either just give up and don't answer it, or you guess and you don't slow down, and you can actually solve this one, and it's actually not that hard if you can take it systematically. So what's the general idea here? The question is, do you know the rules of resonance? Do you know how to convert one resonance structure to another? And the pattern where you can generate resonance structures from a negative charge is when that negative charge / lone pair is adjacent to a pi bond. So we've got that situation here. Lone pair adjacent to pi bond. So I can go move the lone pair over to make a new pi bond between the oxygen that held the lone pair originally and the adjacent atom. But if I stop there, I would have too many bonds to carbon, so I have to move the pi bond onto the other adjacent atom as a lone pair. Now, at first, you're going to think, I am running out of time. The exam isn't timed, by the way, so as long as you give yourself enough time. But at first, you're going to be thinking, I don't have time for this. I need to just be able to see all of it at once. And I will say, just as someone with a little bit of experience, patience, young Padawan, the pattern will be made clear. The negative charge used to be there. Now it's on this adjacent atom. One, skip one, then there's another one. Okay. Now notice that the lone pair here is adjacent to another pi bond. Okay, well, I can do my resonance 2-step, moving the lone pair over to form a pi bond with the adjacent atom. If I stop there, I'd have too many bonds to carbon, so I move this bond over. And, okay. Now notice I'm having to redraw something a couple of times, and that will stress you out, but you'll only have to do it as long as it takes you to figure out what the pattern is. So let's draw our new resonance structure. We have a negative charge here. I've demonstrated so far that it can be on these three atoms. The pattern is one, skip one, the next one, skip one, the next one, and so on. And hopefully you can see that by pushing arrows like that, I could put the negative charge here. hopefully you could see if I push arrows like this, I could get the negative charge there. You see a pattern emerging? Yeah, now now at this point, if I want to, I can go ahead and draw all of the resonance structures, but I can also say with a fair amount of certainty that the negative charge can be on those alternating atoms. Problem solved. So what this is going to be, ultimately what this would look like is I'm going to have option A, B, C, D, Q, and Z, and you'll have to pick which ones have the negative charge. The way I typically ask that question is there's various lists of atoms that have the negative charge, and you have to pick the one that has all of the right ones and none of the wrong ones. I've done more sinister questions in the past where it was a multiple response question, and you've got partial credit for each answer, but anyway, people hate that, I think, in general, so I've stopped doing that. All right. It would be worth your time to try a similar question. I mean, I'm just making this up off the top of my head, but it would be worth your time to go ahead and show yourself that the same types of principles apply if you have a positive charge adjacent to the pi bond. In this case, generating one resonance structure from another involves that kind of arrow, but I'll leave you to that to sort of work out on your own. All right. So lastly, I want to sort of give you a sense for, in the molecular orbital world, where resonance comes from. To do this, we're going to start with a simple molecule, and this will be the first time I think that you hear about this concept. We'll revisit it again in a later chapter, but it's useful to have in mind. This molecule is called the Allyl Anion, and I've numbered the atoms. I'm in some cases implying hydrogens that I'm not showing, and I'm drawing a resonance structure that indicates that the negative charge can be on carbon 1 and on carbon 3. Notice that if I keep the rules of resonance, I cannot draw a resonance structure where the negative charge is on carbon 2. Right? All right, now let's think about first the atoms that are involved in resonance. Let's deal with their geometry. Hybridization of carbon 1 should be what? Sp2, because it's surrounded by three things, so trigonal planar. How about carbon 2? Also Sp2. How about carbon 3? Ah, okay. You fell for it. Many of you are looking at that and saying Sp3. Why do you think that? It's surrounded by four groups, the three bonds and the lone pair, right? Okay, so I agree with you that I agree that it was reasonable to come to that conclusion, but I want to show you why it's not true. Look at this other resonance structure. What is the hybridization of atom 3 in this resonance structure? Sp2. Okay, this allows us. That answer is wrong. No, we're obliterating it. I don't know. Now I'm embarrassed. So one rule of resonance, an important rule of resonance, is atoms do not move. Period. If in resonance we were switching back and forth between Sp3 and Sp2, that's not just an imaginary thing. We would be talking about switching geometry from tetrahedral to trigonal planar. that's going to involve motions of the hydrogens. That's illegal motion in the backfield. That's not allowed, okay? Flag on the play. My sports analogies are very, very weak. I need to consult my sons. In any case, you can't move atoms. Therefore, if it's sp2 over here, it must be sp2 over here. Okay, what does that tell you then about the lone pair on atom 3? In what kind of atomic orbital would it reside? Yeah, that has to be in a p orbital. The lone pair on atom 3 has to be in a p orbital. Now that's not usually true when resonance isn't a thing. For example, with the methyl anion, that lone pair, that methyl anion is sp3 hybridized, and the lone pair is in an sp3 orbital. But when that lone pair is adjacent to a pi bond, that atom is going to be sp2 hybridized, and the lone pair is going to be held in an atomic p orbital so that resonance can occur. All right, so just based on the rules of resonance, we've argued that that lone pair has to be in a p orbital. Great. Now here's the jump, okay? And the jump is that orbitals that line up to each other side by side can interact with each other. So let's go ahead and take a sort of side view of this allyl anion. This is the plane, and whoops, we'll just draw this resonance structure. We'll have the negative charge here. I've just told you that that negative charge is in a p orbital that should be both above and below the plane of the page, or rather above and below the gray plane. Now, how about atoms 1 and 2? What kind of orbital do we have here because of that pi bond? Yep, we've got a pi bonding orbital, which we have drawn before, like that. And remember, when we made pi orbitals before, we combined two p orbitals on adjacent atoms in the plus combination to get the pi orbital, and in the minus combination to get the pi star. Well, now we've got 3 p orbitals lined up side by side. This allows us to do something that we did maybe with methane earlier on. We're going to combine more than 2 atomic orbitals together to get more than 2 molecular orbitals. So we're going to take those 3 atomic p orbitals, and we're going to mix them together to become 3 new pi molecular orbitals. Now, I'm going to draw these orbitals for you. And in so doing, it can be a little bit confusing, and the answers really come out of the math of molecular orbital theory. The MO theory study guide takes you through sort of conceptually how you can imagine these orbitals forming. I'm not going to ask you to predict what these orbitals look like, so don't worry about that. But making conclusions, drawing conclusions based on seeing what the orbitals look like is something that I think is within your reach. And I'm just now coloring in the plane so that you can see the yellow lobes are above and the pink lobes are below. So let me show you the 3 molecular orbitals that come out of this analysis. The lowest energy one is the one where we add the 3 p orbitals on adjacent atoms together, all with the same wave function sign. So there's continuous overlap of the lobes on the top, the orange lobes on the top, and then overlap of the pink lobes on the bottom. Atom 1 is here, atom 2 is here, atom 3 is here. If we were to try to draw what this actually looked like, from the side, we would see a continuous lobe of wave function here above all three atoms, 1, 2, and 3, and then we would see a continuous lobe here below with a wave function, with the opposite wave function sign, and the node is the plane. So this is like an extended pi bond, right? It's like over 3 nuclei instead of 2. And because it's over 3 nuclei instead of 2, and because the electrons in this orbital would be more spread out than in a regular pi bond, this pi molecular orbital is more stable than just a pi bond. So we'll call this pi 1. The next easiest combination to see is one in which you add each wave function, each atomic orbital wave function together, but with minus, but the minus combination where the wave function, where the wave function sign switches as you go from one atom to another. Here's atom 1, 2, and 3. Every time the wave function switches, we have a node, so there's now a vertical node here and another node there. Wave function sign changes as I go from here to here. So this is a higher energy orbital. It basically looks like I've drawn here. And it would make sense that this one is higher in energy than this one because this one has no vertical nodes. They all have the same horizontal node, but this one has no vertical nodes. So those two combinations are pretty straightforward. The other one is the one that's a little bit weird. And in this one, we've got atoms 1, 2, and 3. You've got wave function on carbon 1 and wave function on carbon 3, but no wave function on carbon 2. Because there's a change in wave function sign that actually corresponds with carbon 2, and at that point, wave function equals 0. Yeah? That's right. That's destructive interference at carbon 2. So if this were a sine wave, I would simply say we switched signs and went through 0 at carbon 2. Okay. It's destructive because the other two are opposite in phase, yeah. So you have to look at these orbitals and understand that an orbital in pi 1 would be spread out over pi 1, 2, and 3, about atoms 1, 2, and 3. An electron in pi 2 would only be on carbon 1 and 3, never on carbon 2. All right? So we have to pause there, but what I want you to do is, based on the nodes that we've drawn, I want you to order these orbitals in energy. Then I want you to go back to our original Lewis structure. I want you to figure out how many electrons are involved in resonance. Then I want you to fill up the available orbitals, pi 1, 2, and 3, with the available electrons, and tell me where the HOMO is. Okay, so we'll start off with that next time, and we'll probably do all of chapter 3 next time as well. It's pretty short. So I will see you on Friday.